In this lecture, we will discuss how to design suitable experiments to identify the nature of protein ligand interactions by isothermal titration calorimetry. We have at length discussed that how to choose protein concentration, how to choose ligand concentration. We have also discussed that how to obtain the thermodynamic parameters from an isothermal titration calorimetric profile. And then we further discussed that how to get the values of K, delta H, delta S and hence delta G naught, and in what way these should be interpreted. Obviously, the next question is that if we look at the overall value of delta H naught, it could be either positive or it could be negative. A positive value of delta H naught of binding does not necessarily mean that the binding is only hydrophobic in nature, or an overall negative value of delta H naught does not necessarily mean that the protein ligand interaction involves only ionic or polar interactions. Whenever a ligand binds to a target site, the binding site involves amino acid residues, and those amino acid residues will have some polar character, it will have some hydrophobic character, depending upon the type of amino acids which constitute the binding site. And therefore, when the incoming ligand comes and fits there, it is possible that there could be a combination of the polar interactions and the non-polar interactions. And whatever predominates, the sign of delta H will reflect on that. And that is why when the value of delta H naught is overall positive or the value of delta H naught is overall negative, we say that the binding is predominantly polar in nature or the binding is predominantly hydrophobic in nature. Now, can we design further experiments which can support our claim more authentically about the contribution or establishing the contribution of polar interaction, whether these are hydrogen bonds, electrostatic interactions, or how to identify the involvement of hydrophobic interactions? Let us discuss those issues in this lecture. Let us take a look at again the same slide which I discussed in the previous lecture on the binding of anti-inflammatory drug Naproxen with serum albumin, amitriptyline which is antidepressant, and methimazole with serum albumin. Let us see what kind of experiments can be designed. Now, suppose that the ligand is able to establish ionic interactions at the binding site. What kind of experiments can be designed so that this ionic interaction between the incoming ligand or drug molecule and the protein binding site can be reduced? And this can be reduced if we introduce in the solution something which can interfere in these ionic interactions. That means if we introduced some other ions into the solution which will interfere in the ionic interactions between the ligand and the protein, then it will affect the value of binding constant. it will also affect the values of delta H naught and delta S naught. So, let us think of what kind of additives can be added which can reduce the ionic interactions. One electrolyte that immediately comes to mind is sodium chloride. If I increase the concentration of sodium chloride in solution, the concentration of sodium chloride, many times we also talk in terms of ionic strength. If we look at the literature, people also, when they increase the concentration, when they introduce electrolyte into the solution, they also talk about ionic strength. Let us take a look at what is ionic strength. Ionic strength is represented by the symbol I. And what is this I defined? This I is defined as half summation I Ci Zi square, where the C is concentration, Z is charge. And if one wants to express in terms of molality, then I can also write I is equal to half summation I Mi Zi square, where M is molality and C is concentration. What I have been discussing is that if I add sodium chloride in solution, I can say that the concentration of sodium chloride is this, or I can also express in terms of ionic strength. But a word of caution over here. When you talk about ionic strength, and let us take a look at the definition of ionic strength given over here. It does not say that in calculation of ionic strength of the solution, you only consider sodium ions and chloride ions. Ionic strength of a solution will be calculated by including all possible ions present in the solution. Right? Now suppose if you have only sodium chloride in solution, let us say if I have if I have molality of sodium chloride as 0.01 mole per kg, then ionic strength will be equal to half M plus Z plus square, plus is the positively charged cation, plus Mi minus Z minus square, where Z minus is an ion. I is equal to half M plus is 0.01 into charge on sodium ion is 1 plus concentration of chloride ion is also same, 1:1 electrolyte, 0.1, and minus 1 square is also 1. So this is 0.01 plus 0.01 divided by 2. This is equal to 0.01 mole per kg. That means I can immediately write for 1:1 electrolyte, I is equal to M. But this calculation I discussed over here only to make the things clearer, that if you have only sodium chloride in solution, Sodium chloride is 1:1 electrolyte. In that case, I is equal to M. However, if there are more than 2 ions present in solution, then according to the definition of ionic strength, we need to consider all possible ions in solution. Therefore, this is a word of caution that when we are reporting the ionic strength in a solution, we must include contributions due to all possible ions present in the solution. Now, let us discuss further. As we were talking about introducing something into the solution which can interfere in the ionic interaction. One thing that immediately comes to mind is sodium chloride. When you add sodium chloride in solution, let us see how it affects the binding parameters. Let us take a look at the table. This table is the same table that we discussed earlier, expressing that the binding constant of naproxen with serum albumin is of the order of 10 raised to the power 7. Let us keep in mind. And for amitriptyline, the binding constant is of the order of 10 raised to the power 4. Now, let us take a look at how the binding data gets affected when the concentration of sodium chloride is increased in solution. Let us first take a look at the binding of naproxen. As the concentration of sodium chloride is increased in solution from 0.2 molar to 0.5 to 1, the order of the binding affinity decreases. It decreases from 10 raised to the power 7 to 10 raised to the power 6, and further increase in concentration of sodium chloride, you see, further leads to decrease in the value of binding constant. And this is what I was referring to, that if an additive interferes in the interaction between two molecules, that will affect the value of K. Now, what is happening here is, since naproxen is having ionic character because of COO molecule, COO end, sodium chloride is able to make some electrostatic bonding with the naproxen, and in turn it affects its binding at the binding site. That is why what we have observed, what we see in this table is that the addition of sodium chloride at a higher concentration decreases the value of binding affinity. That means sodium chloride is able to interfere in the electrostatic interaction. So therefore, it establishes that the electrostatic interactions are playing a dominant role in the binding of naproxen with serum albumin, because sodium chloride is able to interfere in this electrostatic interaction. Now, let us take a look at the table again for the data with amitriptyline. Increase in the concentration of sodium chloride from 0.2 molar to 0.5 molar to 1 molar, it did not change the order of binding constant, clearly suggesting that the sodium chloride is not able to affect the binding interactions of amitriptyline with serum albumin. So this suggests that the electrostatic interactions are not playing a significant role or a dominant role in the binding of amitriptyline with serum albumin. So this is one kind of example where in this report the use of sodium chloride in studying the binding affinity suggested that the electrostatic interactions are playing a significant role in the binding of naproxen with serum albumin, but these do not play a significant role in the binding of amitriptyline with serum albumin. Now, if we are interested in understanding hydrogen bonding interactions, similar type of experiments can be thought of. And suppose if the ligand, if the drug molecule has several functional groups which can establish hydrogen bond when it enters the binding site. And before it binds, if we introduced some other additives into the solution which have several hydroxyl groups or several hydrogen bond acceptors or donors, then it is possible that that additive may make hydrogen bond with the drug molecule and hence affect its availability, free availability for binding to the protein molecule. Some examples which one can think of such additives are glucose, sucrose, amino acids, because they can also form hydrogen bonds, or some other molecules which are able to either donate or the other molecules which are either acceptor or donors, to establish hydrogen bonds. Now, if one is interested in unraveling, in understanding whether hydrophobic effect plays a role in the binding of protein ligand interactions, then what kind of experiments can be designed? Obviously, the effort should be to choose the additives which can engage in hydrophobic effect with the solute molecule, with the drug molecule, and hence affect its availability for interaction with the protein. Let us take a look at some example. With sodium chloride, in this particular case, it got established that there are stronger electrostatic interaction of naproxen with BSA than amitriptyline. Then, in this report, surfactants were chosen as additives. Surfactant molecules will have a long hydrophobic tail and a polar head group or ionic head group. The hydrophobic content of surfactant is large. But if one chooses surfactant molecules as additive, one must be careful. Here is a word of caution. It has been observed that the surfactant at higher concentration can lead to denaturation of the protein. Because the surfactants have higher hydrophobic group, and the hydrophobic, because of that hydrophobic content, it can interact more with the denatured state of the protein and hence shift the native to denatured equilibrium towards right. Surfactants have been observed to denature the protein above a certain concentration. Therefore, if we want to choose surfactants as additives in the protein ligand binding studies, we should take an appropriate concentration of surfactant which does not affect the integrity of the binding site, and that should be established by independent methods. We will discuss about those later. Let us first take a look at this table. The table gives the thermodynamic parameters associated with the binding of naproxen with serum albumin in presence of SDS H-tab is a cationic surfactant. SDS, sodium dodecyl sulfate, is an anionic surfactant. TX100, tritone X100, is a non-ionic surfactant. Anionic surfactant, cationic surfactant, and tritone X100, which is a neutral surfactant, non-ionic surfactant. In presence of sodium dodecyl sulfate, the concentration of sodium dodecyl sulfate in this experiment, in this report, was taken as 8.5 millimolar. It was observed that the binding is completely lost. As long as SDS at this concentration, 8.5 millimolar, does not lead to the denaturation of the protein, it establishes that the ionic interactions are significant because it has sulfates, negatively charged end. And you see, it gets a support to this conclusion because the non-ionic surfactant is not interfering in the binding to a large extent. It has only reduced the binding affinity from 10 raised to the power 7 to 10 raised to the power 6. Similarly, experiments can be designed with amitriptyline to understand that what kind of interactions are predominant in the binding of the drug with the protein. In short, by a suitable choice of the additives and doing the isothermal titration calorimetric experiments, the comparison of the data suggests in further establishing the relative contribution of individual type of interactions in the overall binding process. Now, it is possible that the different drugs may go and bind at the same binding site. Sometimes the drugs are given in combination. And if one is interested in understanding that whether the individual drugs go and bind at the different binding sites or these drugs go and bind at the same binding site, can isothermal titration calorimetry help in understanding this? The answer is yes. So, how does one proceed? Amitriptyline, which is an antidepressant, and Naproxen, which is anti-inflammatory drug, are sometimes given in combination. And therefore, it will be of interest to understand whether these drugs go and bind at the same binding site or they bind at the different binding site. How we can design the experiment to understand this? What one can do is, you form a complex of serum albumin with naproxen and titrate with amitriptyline, and vice versa. And then one can compare the value of binding affinity. Now, suppose if the binding affinity is not affected at all, what I mean is, you form a complex of the drug with serum albumin and titrate with another drug, and if the binding affinity is not affected at all, that means the incoming drug is going and binding at some different binding site. And if the binding is affected, if the binding affinity is reduced, that means there is an overlap of binding site. Let us take a look at the data in this report. What was done is, the binding of naproxen and amitriptyline with serum albumin was studied in presence of each other. That is, amitriptyline BSA complex was formed and it was titrated with naproxen, and the resulting isothermal titration calorimetric profile yielded the data presented in this table, where you see the value of K remained of the order of 10 raised to the power 7, although the absolute number decreased to a small extent. Whereas for amitriptyline, when it was titrated to naproxen BSA complex, it remained of the order of 10 raised to the power 4. One thing is there, that if a site is occupied by a ligand which is weakly bound and another ligand comes which has a strong affinity at the same binding site, that will displace this molecule. Now look at this table. Here naproxen is titrated with amitriptyline BSA complex. The value of K remains of the order of 10 raised to the power 7, although there is a slight change in the absolute value. But when amitriptyline is added to naproxen BSA complex, the value of K is remaining nearly same. So what conclusions can be drawn? Is naproxen binds to BSA with reduced affinity, and amitriptyline also shows a slightly decreased binding affinity, a slightly decrease, only a slight decrease which is there in the absolute value. So based upon such kind of experiments, conclusions can be drawn whether the drug binds at the same site or at the different site. As I mentioned, if the drugs bind at different sites, then the complexation of the protein with one drug molecule will not affect the binding affinity when it is interacted with the other drug molecule. And when they bind at the same site, then the value of the binding affinity will be affected and the values of the binding thermodynamic parameters will be affected. So therefore, isothermal titration calorimetry can also assist in establishing whether the different drugs bind at the same site or the different drugs bind at the separate site, different sites. And in this case, in case of naproxen and amitriptyline, this forms a nice example of making a study in this direction and getting some useful results. The main conclusions from this report was that naproxen interacts mainly via electrostatic interactions and amitriptyline interacts mainly via hydrophobic interactions. So what we discussed in today's lecture, that isothermal titration calorimetry not only helps in giving us the quantitative numbers on the binding thermodynamic parameters, it also helps us in identifying the nature of intermolecular interactions. One is that identifying the nature of intermolecular interactions based on the overall values of delta H naught or delta S naught. And second is to get further insights into the relative contribution of individual type of interactions. Suitable experiments can be designed by choosing variety of additives so that we can try to understand that what type of interactions, whether the hydrogen bonding interactions and electrostatic interactions hydrophobic effect or some other type of interactions possible play a dominant role in the binding process or not. Isothermal titration calorimetry can also be used to establish the binding site. Of course, the binding sites, where is the binding site, the nature of binding site actually is well established by X-ray crystallography. But if we know that a given protein has more than one binding sites from incoming ligands, isothermal titration calorimetry can help in establishing that the incoming ligand is binding at site 1 or site 2, or if there are more binding site, then it goes to which binding site. And that is by using the suitable site markers. Suitable experiments need to be designed in this direction, and how to design those experiments, those issues we will discuss in the next lecture. Also, we will discuss that how the binding of a ligand molecule to a drug molecule affects the differential scanning calorimetric profile, and how to interpret those differential scanning calorimetric profiles to get more information about the binding process. Those we will discuss in the next lecture. Thank you very much.